All right, in this video, we are going to discuss similarity in right triangle standard number 1, which is basically about doing dilations on point, line, play, points, lines, rays, and segments. The two main types that we have to be focused on, if the center is at the origin, we have shortcuts based on arrow notation, which we discussed. And the primary focus for this video is if it's not centered at the origin, although we'll do a quick recap of our previous work. So, dilate a point centered around the origin 0, 0, using a scale factor of 1.5. We discussed previously that since it's centered at the origin, we just have the quick arrow notation shortcut, multiply both the coordinates by the scale factor. So we'll take -2 times 1.5, and we will take 4 times 1.5. As Jerica told me, when we multiplied those two numbers by 1.5, -2 gets moved to -3, and 4 gets moved to 6. So we'll just plot that point and say 3 to the right, 2, 4, up 6. I want 3 to the right. It's supposed to be 3 to the left. I don't know why I did that. That's just silly. 3 to the left, and then up 6. And then we've got our point A prime, located -3, 6. I would like to re-emphasize, you can't really see the changes going on, but there is an undrawn segment and an undrawn triangle from the center to the point for both the pre-image and the image. Those create similar triangles based on the dilation. I'd like to emphasize another component that I didn't mention previously. The gaps between the center and the point. This was a gap of 2 left and a gap of up 4. Well, those gaps became times 1.5 times 1.5. It became a gap of 3 and a gap of 6. I'm emphasizing these gaps because when we start doing pieces that are not on the origin, it's the gaps that will be important, not the coordinate numbers that will be important. So let's continue with the dilation of a segment. Centered at the origin, let's take advantage of our shortcut. To use a scale factor of 2, where does the point A get moved? -4 and 8, so we'll go 1, 2, 3, 4, 2, 4, 6, 8. And we've got A prime located at -4, 8. Once again, I want to emphasize this, and I'll erase this in a second. A gap of 2 to the left was increased to a gap of 4. The gap of up 4 was increased to a gap of up 8. Those gaps are getting made bigger by our scale factor of 2. And let's also move point B. Point 2, 2. So B prime is located at 2, 2. And we could simply connect the dots, connect those points, and we create our segment. Please remember the important characteristic. Those are parallel. Whenever we do a dilation, segments will be parallel to each other. So when you draw it, if you see that they're not parallel, that's an immediate red flag to let you know something went wrong. You need to have parallel, and it's a quick check to see that you were doing things correctly. All right, continuing with a scale factor of 3. Same thing, we'll just multiply by 3, so 2, 4, 6. At this point, I'd like to note, do you notice how there isn't a left and right gap in terms of like lines with slope? There isn't a run component to it. Well, basically, the gap for the left and right is 0. What happens if you triple 0? And so this is actually showing that as well. And let's triple our B for our dilation. -3, -6, so 1, 2, 3, 2, 4, 6. And then that's B prime, -3, -6. And we'll see how badly I can sketch this. There's our ray. Of course, making the observation that dilations don't change what the thing is. Points stay points. Segments stay segments. Rays stay rays. The behavior of the figure does not change just because we've dilated it to make it so-called bigger or smaller. And one more here. Dilate the line by a scale factor of 1/2. So where does point A go?
1 and 2.
Well, half of -3. Half of -3 is -1.5. Half of -2 is -1. So left 1.5, down 1. We'd get our A prime, the image of A. And we likewise need to move point B. So 1 to the right, up 2. And now we need to connect, and since it was originally a line, it's going to stay a line. Fortunately, this one's a little bit easier because as a line, I can just try to make certain I keep it parallel. Doesn't mean I'm going to be good at keeping it parallel, but that's what I'm trying to do. And so we have those finished up. Each one of those things was using the origin as the center, which allowed us to take advantage of arrow notation shortcuts. Unfortunately, that will not always be the case. Dilate the point M using +2, -1 as the center for the dilation, and a scale factor of, well, let's just say a scale factor of 2. The important thing to keep in mind, it's not just the numbers that get changed. It's the gaps, it's the size, it's all those pieces. We have to keep in mind that from here, we'd have 2 to the right, down 1. This is the location for our center. And so everything we do is based on increasing the size of the gaps from that point. We can make the observation that this triangle, the undrawn triangle that we always kind of think about, is going to be resized using our factor of 2. So this piece, which was 2 up, is going to have to be resized to be 4. Likewise, this piece on the bottom, which is currently a gap size 4, the gap gets resized to 8. And so we can think through the resizing and simply say 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. And that's where it gets moved. Resizing the gaps is the focus behind our dilation. Well, I am curious, what are the coordinates for our image of M? One, 2, 3, 4. 1, 2, 3, 4, 5, 6 to the left. 1, 2, 3 up. And of course, we should be able to quickly identify.
Negative 2 times 2 is negative 6.
Now, I'd like you to stop off for a second and consider our quick rule that we were using earlier of just doubling the numbers. Is it working here? No, because, well, think about why. Why doesn't that rule work anymore? Consider what we had before when we were focusing around the center. When we had this point of negative 2, 4, the numbers here, when we graph in the coordinate plane, those numbers are based on their relationship to the origin. Basically, it says start here, go 2 left, and up 4. Well, when we change the center, we're still not, or rather, we're not focusing on coordinates being away from here. We're instead focused on away from there. Basically, if we use the origin for the center, the numbers are already recording the size of the gaps. But if we pick a different center, then it's a different size gap, and we have to pay attention to that. That clear up your question a little bit, Jerica? Okay. Well, let's continue that same idea. And I would like to see you, people at home, pause the video, try out this problem on your own. All right, in class, understandably, we're seeing some confusion, and I'm seeing a lot of people using the origin as the center. The key feature that we have to keep in mind is all the gaps are based from the center that we're given. So when we are told to use negative 2, negative 3 as the center, we have to pay attention to the size of the gaps from there. Now, it's not necessary or required to write down these undrawn triangles. I'm putting them down just so that you can see my thought process. Although if you do the same part mentally and you don't need to draw the triangles, it's completely acceptable to do that. The part that I'm observing is that I have a gap going up and a gap going over to that point N. When I do this dilation, we know that the undrawn triangle is going to get moved by a scale factor of 1/2. So each of the gaps become 1/2. In this one, I have a gap of 3 for the side of the triangle. And likewise here, I have a gap of 3 for the sides of the triangle. Each of those gaps get multiplied by the scale factor. 3 times 1/2 is going to be 1.5. So this tells me then each of the gaps going up needs to be 1.5, going over needs to be 1.5. And that's how I can determine where my point N prime will be. It will come up 1.5 and over 1.5. This is the location for N prime. And unfortunately, there's no shortcut to determine the coordinates. Yes, thank you, Jerica. I don't know why I did 2.5. Thank you for catching that. Backing that part up, I went 2.5 over. It's only supposed to be 1.5. So there. Now, there is no shortcut for determining the coordinates here. There's no quick just multiply by 1/2 rule. We actually have to look at where it is and read the coordinates. In this instance, it's 1/2 to the left and 1.5 down, so -3/2. That's a tough 2 to read.
So negative, huh?
Yes, the first coordinate is negative 1 over 2. The second coordinate was negative 3 over 2. Now, to finish this and draw our segment, we need to do the same process to the other point M. Now, if you need to, go ahead and draw the triangle from the center to point M. If you don't need to do it and you can just count and do it mentally, that's also completely acceptable. People at home should pause the video and try doing it. In class, you should too. All right, since I don't need this other stuff from here, I'm going to erase these pieces that work I don't need. All right, here's the thought process. From the center to point M, there are gaps. The gaps need to be resized. So we will have to pay attention. There's a gap down and there's a gap to the left. How big is this gap going to the left? All right, so the gap of 2 left needs to be multiplied by that half. How big of a gap is it going to be resized to? All right, so half of 2 is 1. So when we resize the gaps, the new point, the image, is going to be 1 to the left of the center. We also need to resize the gap going up. How big is the gap going up? Okay, since this is 8, instead of going 8 up, we're going to go half as far. So 4. Looking at those 2 gaps and resizing them, we should be able to identify that the new point, the image of M under this dilation, is going to be 1 to the left of the center and up 4 from the center. Thus, all we have to do is to count 1 to the left, 1, 2, 3, up 4. And that's where our point got moved. M prime was located by dilating the gaps from the center and the pre-image point. And so we would have this located at negative 3, 1, allowing us to now connect the points. And once again, what do you notice about the 2 segments? They're parallel. As we know, segments will always be under a dilation. Now, like we saw yesterday, segments are of course the most important one because if we're doing a ray or if we're doing a line, it's the same thing. It's the same thing for lines and rays. We just treat them like segments, do the 2 points, and then keep the same kind of a behavior. All right, so let's get a little bit. All right, so let's dilate this segment using the point negative 2, negative 3 for the center, and a scale factor of a half. So once again, let's use this process of paying attention to the gaps and changing the size of the gaps. Where is the center going to be located? Negative 2, negative 3. So there's the center. Here's an interesting bit. We still need to figure out where the image of n will be. Where is n prime supposed to be? And so we have to pay attention of the gaps from n to the gap of the center. Well, how big are the gaps? Absolutely, Kalani. the gaps are 0. The center is the point N. So if we have to take those gaps and make them half as big, what happens? Where does point N get moved? Yeah, you've got it. It doesn't get moved. The image is actually exactly where it needs to be. And it's kind of tough to, we really can't draw it very well, because how do you draw a gap of 0? As soon as you draw anything, you've made the gap bigger than 0. So it can't be drawn. You just have to understand, if the center is actually a point, the center will never get moved under a dilation, because it's always a gap size of 0, and 0 multiplied by whatever scale factor you want is still going to stay 0. Of course, this point M doesn't have that. Where does point M get moved? All right, people are telling me -2 and -2.5. Right, I'd like to go through the work and verify. Just -0.5? Okay, so -0.5. Okay, apparently I wasn't understanding 2.5. Okay, so let's verify your work then. Fine, I'll fix the ugly looking 2. Positive 2.5. Okay, so this one, we have a gap of 2 becoming a gap of 1. And this is a gap of 8 becoming a gap of 4. So 1 to the left, 1, 2, 3, 4. So not 2.5, but 2. And so M prime is located at -3, +1. Those are the coordinates for it. There's one other observation that we should make here. This segment is our dilated segment. Why don't we have parallel segments, or why can't we see obviously parallel? One of the things to keep in mind when we were doing our dilations, we saw that gaps got made bigger. For instance, a gap of to the right, or a gap going up, and I realize this one isn't based on the center, but when we had gaps going right and gaps going up, what wound up happening is those gaps left and right got made bigger and bigger. Because this one had a point that was fixed, the center didn't get moved, what wound up happening was those gaps that got moved actually wound up falling on top of each other. This is behavior that will happen every single time your segment, your line, your ray, if a segment, line, or ray passes through the center, the image is going to fall on top of the original pre-image, or at least in part. You'll wind up you'll wind up dilating the size of it, but it's still going to have the same kind of direction falling on top. Let's see that here, and this is our last example for the day. Dilate the line using the center of 0, 0. Well, please note, since it's 0, 0, what are we allowed to do? Because it's centered at the origin, or just multiply by the numbers shortcut works. Because it's at the origin, we don't have to count the gaps the numbers in the point are already recording the gaps for us. That only works with the origin, so we can just quick multiply the numbers.
Whenever it's 0, 0.
Correct. Whenever the center is 0, 0, also called the origin, whenever the center of the dilation is these 0.00, we don't need to record the gaps. We can take advantage of the shortcut, just multiplying the numbers. So let's multiply the numbers and see where we get. Point A goes to 6, 3. There's A prime. And let's move point B. -3, -1.5. Thank you for giving me the numbers. And so what do you wind up seeing? Exactly, it's the same line. And it's not an accident that this happened. Our center was right here. And the line passed through the center. Whenever we have a line, a ray, a segment going through the center, it's going to maintain the same direction. It's going to maintain the same location. All we do is kind of stretch it out longer or shrink it down in terms of size. Except in this instance, when we talk about a line, lines have infinite length, so we still wind up going on past our point, continuing the trend forever. And for this one example here, the dilation goes exactly on top of where it began. It just kind of stretched out the line. And so we finished up our work today. This covers everything we needed for similarity and right triangle standard number 1. Our unit has 3 standards. This is one of the 3 standards. Being able to do dilations on a point, a line, a ray, a segment, and it shouldn't matter if the dilation is centered at the origin or centered at some other